Hello and welcome to Lesson 5, and today we're looking at the introduction of kinematics. So we've been working and focusing on vectors and scalars, and more specifically vectors, and now we're going to look at some of the motion, the equations behind motion, where we'll see vectors starting to tie in. So today's goal, I can differentiate between vectors and scalars and explain the associated terminology. So now we're looking at vectors and scalars in terms of applications in the real world. So I have some definitions to go through. It's really beginning to introduce a new topic here. So terms and definitions, very, very important, because when I am assessing your tests or your assignments, I'm looking for you to be using the correct terminology. Same thing with oral, when you talk to me or give oral answers, I'm looking for the correct wording. So you see two terms here to start off with, distance and displacement. The definition of distance is simply how far an object travels. Now, this is a scalar value, and simply put, we are asking how far did you go today, how far did you drive, how far is it to Stratford. Okay, that's considered a distance because, again, no direction is being given here. All right. Now when you move on to displacement, displacement is distance's partner, and it is how far an object has traveled relative to its starting or reference point. So this is a vector, okay, because direction is important here, or direction is needed. So how do we differentiate between the two? All right, so a simple example that I use, here's our reference points. Let's say that you started at home, you then traveled to school, which is, keep it easy, 10 kilometers. And then at the end of the day, you returned home and traveled another 10 kilometers. So your distance, D, is a total of 20 kilometers. Same scenario down below with displacement. Travel to school, 10 kilometers. When you're at school, you walk around. Now you return home at night, 10 kilometers. If home is your reference point, and that's what you're measuring it from, our displacement, which is a D with a vector on top, so D for distance and D with the vector symbol for displacement, is 0 kilometers, because you are at the same location you started at. So that's relative to your reference point. Now when you were at school, just for argument's sake, at school, your displacement was 10 kilometers, and I'm going to say east or to the right because you need to have a direction. Okay, whereas with distance, your distance was simply, oops, almost put the vector symbol in, your distance is 10 kilometers. No one is concerned with the actual direction. So that's the difference between the two. As we move on here, we get to speed versus velocity, and again, they're partnered up. Speed is your change in distance of an object over a given time period. Okay, so again, speed, and we use the letter V, all right, and we are looking at distance divided by your change in time. So there's your formula, and we're gonna put a whole bunch of formulas down here in a little bit, so it's not too important at this point. But that is what we're looking at. Speed is the change, and V stands for, I know it seems like it should be for velocity, but because there's no vector symbol on top, it is speed. Whereas velocity is the change in displacement over a given time period. And we write this as a vector now, so that's now velocity, which means we need to have a vector on the other side being divided by time. All right, so speed is just looking at how fast you're going. Velocity is how fast you're going and what direction are you traveling. Acceleration, probably a new term for us this year. Acceleration is the rate and change of velocity over time. So basically, how fast am I speeding up? So we're looking at how is your velocity changing after 1 second, 2 seconds, 3 seconds, and so on and so forth. So how fast am I speeding up is what your acceleration is. And the units, just put that in here, is meters per second squared, and I'll talk about where that comes from a little later on in this video, or at least the next one. Average speed definition, the change in distance within a given time interval. So basically here, the formula would be delta D divided by delta T. And remember, delta D is D2 minus D1, so you're not necessarily starting at the beginning. You're starting partway through, possibly. Average velocity, it's now the change in displacement with respect to time. Similar formula, delta D over delta T. And finally, instantaneous velocity. And that is the change in displacement at one moment in time. All right, and that's the key right there. It's happening at one moment in time. So that's going to pose a challenge when we talk about non-uniform motion in a later video. But for today, it doesn't pose as big a problem. As we move on, I got an example here. So we have Mark. He's running around a 400-meter track. He does it in 10 minutes. Not overly impressive, but more my speed. Mainly just keeping the math simple here for us. So he ran around the 400 meters. So here is, we'll put this as the starting point, and it also serves as the finishing point. And we'll have Mark making a left turn. That way the NASCAR people in here won't get confused. They're making left turns, so they're happy. So if Mark is running around a 400-meter track in 10 minutes, what is the distance that Mark ran? So what is his distance? Well, if he made one loop of the circuit, then he traveled 400 meters. Okay? Now what's his displacement? And remember, his displacement is how far is he from where he started from. Now if the finish line and the start line are at the same location, that means his displacement was 0 meters. And I don't have to give a direction because it's a zero vector. So his displacement was 0 meters. So distance and displacement are significantly different, so it's important that you understand the difference. What was his average speed? So average speed is his distance over time. So that would be 400 over 10, or dividing that down, it would be 40 meters each minute. So not exactly a torrid pace, but that's how that would calculate out. And finally, his average velocity. His average velocity is his displacement divided by time. Sorry, just displacement divided by time. And his displacement was 0 over 10. So he traveled 0 meters per minute in terms of displacement. Okay? So a huge difference between the two. So it's very, very important that you keep those separated as you go through. Let's talk about a position time graph. So DT or PT graph, distance time, it's also known as distance time, and I do switch back and forth, so it means the same sort of thing. Position's the correct terminology though. All right, so what I have here is a position time graph with some information, and I want to answer some of the questions that are provided. So if I look at the graph itself, the graph starting at 0, 0 means that I am starting at one particular point, and because it's a straight line, I'm moving away from that point at a constant velocity because it's a straight line, so nothing's really changing. I'm doing something the exact same all the way through. So just reading off the graph, at t equals 3 seconds, how far away are we from our start? So this is just kind of reviewing how to read the graph. So here's 3 seconds. I go up to that point on the line. I then find its corresponding time, and you'll notice my grid's off a little bit, so that's actually 5, 10, that's actually 15 would be the answer. So we're 15 meters away from our starting point. At 7 seconds, so you find 7, you scroll up, scroll across, 20, 25, 30, 35, that actually fixed itself, so we're 35 meters away. So we are just measuring, just reviewing on how to review a graph or measure a graph. So what does the slope represent? What does the slope represent from a position time graph? So I'm just going to put some information in here. So recall from grade 9, and you need to bring your grade 9 math skills in here. Grade 9, we said that slope is delta y over delta x. So that's no problem. So we have a triangle that's formed here. up above. If we take the 2 points that we did in question here, so we'll form our right angle triangle, and because we have a graph, we can just read the information off the graph. Here's my delta y. Here's my delta x. So my delta y would be the distance from here to here, so it's that vertical distance. So it goes from 15 to 35. So that would give me 20. And I'm going to record the units, meters. Delta x goes from here to here, so from 3 to 7 seconds, so it would be 4. So I can fill in the information below, and in grade 9, you would tell me that the slope is 20 over 4, the slope is 5. In physics, we've got to take it one step further because the units are very, very important for us. So I need to carry those units down because I want to do a unit analysis, and I find that I have 20 meters, and the time is measured in seconds. So when I do the 20 divided by 4, it's still 5. The units are meters per second. So what is meters per second? Meters per second is a measurement of, and I'll give you a hint for those that don't recognize meters per second, you will be more familiar with this at the side of the road, kilometers per hour, and it's a measurement of speed. Measurement of speed, and in this case, I'm going to put or velocity. We're more interested in the velocity. Okay, so it's speed or velocity. So therefore, slope of a PT graph will determine velocity. Very important for us in this early part of the unit. Will determine velocity. All right, so we're going to box that because it is very, very important. And I'll cut off this video here, and I'll finish up a short segment in the next one, and then we can move on.